Well, this is Mr. Yeager, starting with chemistry now. What we're looking at here is actually just some of the mathematical and lab skills that we will need throughout chemistry. In this video, I'm going to be looking at scientific notation, significant figures, and accuracy and precision. All right, and these things are just going to continue to kind of find their way throughout the year as we're working through this chemistry course this year. All right, so starting off with scientific notation. Scientific notation is basically a way for us to rewrite a very, very large number or a very small number into a more simple form. Okay? Scientific notation always basically has, always has a number that's between 1 and 10, basically, more specifically, 9.99999. It has to be a single digit, but it can have a decimal behind it, okay? But it can't be above 10, okay? Or less than 1. So a number between 1 and 9.99999 times 10 to some exponent, okay? This number right here is often called the coefficient, just so we have that term, okay? The coefficient. Scientific notation has a coefficient and then times 10 to some exponential power. So the thing is that we're basically doing here is we're going to take numbers, we're going to move the decimal point until there's only one digit to the left of the decimal point, and then we have to rewrite the number and include an exponent at the end. So the only part that I obviously have some students that do struggle with a little bit with it is what's the exponents, all right? And they get confused because this can be a positive or a negative exponent, and that's telling you which way you're moving your decimal place. So I have a general rule that you're going to see me follow as we do some problems together. If I increase the number, in other words, when I move the decimal point, let me include that in here. When I move the decimal point, if the number gets larger, and again, you'll see this in a moment of what I mean by that, the exponent will get smaller. We basically, as each time you go up a number and move the decimal point and it gets larger, the exponent's going to go down. And then vice versa. If I decrease the number, I'm going to increase the exponent. Okay? So what do I got here? So I mean, that's it. Those are the two things we basically need to understand, and then we go from there. So what if I have these numbers, these examples in front of me? Okay, you can see they're very, very large numbers. All right, and we don't really like that. If we can try to decrease the size of these numbers, we will. All right, so we don't see a decimal point. That would be actually kind of your first step, is find the decimal point. Well, these don't have a decimal point because we don't write a decimal point at the end of the number unless we actually have some decimals. Okay, we have some digits in the 10th, 100th, thousandths place, etc. So we need to put in that decimal point for all of these numbers. Okay, and then what we're going to do is basically move this one at a time. Obviously, as you get stronger at this, you can do it a lot faster and you can just see it. But what we do is we basically are moving the decimal point one digit to the left. Okay. So I'm moving the digit to the left, okay? Now think about my rule here. Let's go until there's only one digit left to the left. So I'm going to move it again, and I'm going to move it one more time. Now I have a number that's 5.8, okay? 5.8. And I'm actually not writing those additional zeros. We're going to get into that in a moment. They're not significant figures, okay? So we don't include them. So 5.8. So what happened to my number? It was 5,800, but now it's 5.8. So my number has gone down, which means my exponent's going up. So this is going to be 5.8 times 10. How many times did I move it? 1, 2, 3. 5.8 times 10 to the third, positive 3. We don't need to write the positive, it's assumed, but 10 to the third, 10 to the 3. Okay? And that's it, and you've done it. You now have your number in scientific notation. If we keep going, 1, 2, 3, 4, 5. My number is now 4.5, so my number is getting smaller, so this is going to be a positive exponent. And this would be 1, I just said it, 2, 3, 4, 5, so times 10 to the 5th. I should write my units, meters, meters. Okay, this one right here, 1, 2, 3, 4, 5, 6, 7, 8. I only want one digit. I have seen people, well, they'll stop right here and they're like, I got to the number. No, we go all the way until there's only a single digit left. So this would be 3.02 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. I've heard other teachers sometimes say count the wells, like these are little wells that are being made. But that's basically what we do with it. 3.02 times 10 to the 8th. All right? So that's showing you the bottom rule here of the number getting smaller, the exponent getting higher. If I keep moving that decimal point to the left, my number, quote unquote, is getting smaller, even though this value is equal to the one above it. They're both the exact same number, just in different forms. Okay? So let's go to another page here. We got ones now that are decimal numbers. So these are very, very small numbers right now. So in this case, I'm going to move the decimal place over to the right. It's very clearly there. I see it. And I'm going to move it over to the right. So 1, 2, 3, 4. I'm going to stop right here, though. I have one digit now to the left. And so this is 5.08 times 10. Well, my number was 0.0005. Now it's 5.08. So my number's gone up. So my exponent must go down. 1, 2, 3, 4. Negative 4. And so I get a negative exponent. That's a negative exponent is telling me that I have a smaller number. Okay? Next one. 1, 2, 3, 4, 5, 6, 7. This is 4.5 times 10 to the negative 7. Again, I'll write my units here. I'll be good. And then this one. 1, 2, 3. 4 times 10 to the negative third kilograms. All right, I'll show it one more time so we're clear. I just move my decimal point. 1, 2, 3. I need a digit to the left of the decimal point. That's why I kept going at the end there. It's 4. My number's gotten larger. My exponent decreases, so 4 times 10 to the negative third. All right, so that is the basics of scientific notation. Now let me point this out just real fast. What if I had to go from scientific notation back? So let's say I have a number of 2.1 times 10 to the fourth. Okay? I write out 2.1, and now I have to decrease my exponent back to 0. So if my exponent goes down, my number must go up. To make my number larger, I have to move my decimal point to the right, and in this case 4 times. So 1, 2, 3, 4, and then fill in zeros. So 2.1 times 10 to the fourth is 21,000. They're the exact same number, okay? So that's why we can do this very, very simply in reverse. You just flip the rules over, okay? Where you try to go, okay, I need that. Well, it's not even that you're flipping the rules. You just follow what it says. If my exponent decreases, my number should increase, okay, and so forth. If I did this as 2.1 times 10 to the negative 4, well, now I have to raise my number, my exponent back to 0. If my exponent's going up, my number must go down. So 1, 2, 3, 4, 0, 0, 0. This is 0.00021. These are equal value numbers. All right? So that is scientific notation. Next, let's look at what's called significant figures. All right? This is an interesting little idea in terms, one very much used in chemistry labs, okay? And it should be kind of used in all science labs. I don't necessarily use it as much in my physics class, but if you're in a laboratory, you are using significant figures, or you want to, okay? So the point of significant figures is the significant figures is telling you how precise is your instrument. Okay, so we're going to talk about precision a little bit more later, but it's basically saying what can your instrument read to? What number could it possibly read to? All right, and so this is kind of a counting exercise. We're basically just pointing out how many of these digits are significant. And again, there's a kind of a funny little rule that we can use that I always continue to use with it. Okay, so what you want to do is first, again, this is very much related to the decimal point, okay? And that's where my rule is going to kind of come about here. So I'm going to erase this real quick. For my rule, okay, if there is a decimal point present, this is called the arrow rule. Sorry about that. I use something called the arrow rule. okay? And again, this is something where you might use it at the beginning and you figure out how it's kind of used. It's meant to be a visual, and you can figure it out without it once you really got the hang of it. All right? So what you're trying to figure out is, do you see a decimal point? If you say that it is present, if you see a decimal point, you're going to start an arrow from the left side going toward the right until you hit a non-zero number. Okay? Follow along with me. You're like probably like, what? Okay? If you see that there is no decimal point, it's absent, we're going to start from the right and point back to the left until you hit a non-zero number. This is sometimes called the Pacific Atlantic technique. I don't even know if it's really called that or not, but I know teachers use the idea of, like, think of the Pacific and the Atlantic with the United States. The Pacific's on the left, the Atlantic's on the right. If you're present P Pacific, your arrow is going to come from the Pacific inward. If there is no decimal point, it's absent, it's coming from the Atlantic, it's going toward the left. And again, we're going until we hit a non-zero number. So this is just an identification tool that we're using right now, is how many of these digits are significant. So I have my first number here, 310. I do not see a decimal point. There is no decimal point there, okay? So what I'm going to do is I'm going to come from the Atlantic. It is absent. So I start my arrow over here, and I start running it until I hit a non-zero number. So that's 0, so I'm going to go through that and stop right there. Everything after that number, everything starting with that number that you stopped at and beyond is now significant. So there are 1, 2, 2 sig figs. And that's it. That's all we're doing. We're not trying to do any more math than that. It's not even any math. It's just an identification tool. Okay? So this first number, 310, has two significant figures in it. Okay? If I go to the next one, I'm going to go below it, 7.324. There is a decimal present. That means I come from the Pacific, and guess what? I got to stop at the first number. That means this number is significant and everything after it. So 7.324 has 4 sig figs, 4 SF. All right. So decimal, come from the left, 0.00560. I come from the Pacific. I keep going all the way until I hit 5. Now I count everything after it, including the 0. I didn't cross it out, so now that 0 is significant. So this one has 3 sig figs. 0.00560 has 3 significant figures. What we're basically saying is, I could measure to this place. What's that? The 100,000th place? The 10,000th place? 100,000th place, right? All right. So that's what we can possibly measure to. All right. 4 million. There's no decimal, so I'm coming from the Atlantic. It's absent, and I go through all those zeros. Only the 4 is significant, so there's 1 sig fig here. I'm not saying that 4 million becomes 4. I'm just saying out of all of those numbers in the number 4 million, only 4 is the significant figure. 0.01000. I come from the Pacific because there's a decimal point present. I stop at the 1, and then there's 1, 2, 3, 4 sig figs. This one right here, I have a decimal present. I come from the Pacific, and I'm going to stop at 4. So everything here is significant. Instead of coming from the right, there's a decimal. I have to come from the left, so this one actually has 5 sig figs. So it's a strange rule involved. It's something that you probably need to practice a little bit, but it's one where all we're looking at, and I think people just make more out of it than it needs to be, is do I come from the left side or the right? And it depends on if there's a decimal point. And that's all. Okay? So let's keep going a little bit. Sorry. Here we go. All right. But one thing we'll definitely have to use it some is it's going to show up in our math. So it depends on whether you're adding or subtracting or multiplying and dividing in terms of how you're going to figure out your significant figures. And you're rounding, okay? Part of the significant figure stuff is that you're rounding to the correct digit, okay? So for adding and subtracting, The rule is you basically just round to the smallest decimal place that you see present. Okay, you round it off to the smallest decimal place. Okay, so if I look at my first number here, I'm not sitting here counting up all the sig figs. I, in the end, am just looking at the decimal side. So this first number has 3 decimal places. The second one has 2 decimal places. I'm just going to put a check mark. And the last one only has 1 decimal place. So I'm going to add all these up. This would be 4, 4, 11, 13, carry the 1, 8, 10, carry the 1. This would be 80.344. That would be after I add up all the digits. But because this last one only has 1 number after the decimal place, I need to round at this number right here, at the 3. So I'm going to keep the 80, but it's going to be point. I have to look at the digit next to 3. It's 4, which is less than 5, so it stays as 3. And so I would round this addition problem off to 80.3. In other words, we basically have to go to the number that has the least precision with it, is what we're looking at, and basically saying the least precision from the decimal standpoint. Okay? So that's where we're going. If I look at this one, go ahead and subtract it. This is going to be 4. Got to take that away. 10, 9. Got to take that one. This would be 2, 2, 2. 222.4 would be my answer. But while the first number has 1 digit after the decimal place, 78 has none. So therefore, I have to cut it off at the decimal point, basically. I'm going to get rid of it, but I have to see if I have to round. So it's 220, well, it's 4 again, so I don't round it up, so I keep it 2. So my answer is 222. So adding and subtracting is just rounding it off to the smallest decimal place. Okay? Multiplying and dividing. This is going to be more common in what we're doing here. Okay? In multiplying and dividing, I have to look at what numbers are involved. Okay? I'll go ahead and mention this now. This might cause some confusion. We don't pay attention to constants. Okay? It's numbers that we have measured that we're going to determine what's the least number of sig figs. Okay? So for this, I'll need my calculator. For multiplying and dividing, I have to round to the least number of significant figures, not decimal places, sig figs. So this is where you need to understand how many sig figs are present and so forth. So my first one here is I have 7.20 times 0.50. The first number has 3 sig figs. The second number has 2 sig figs because they'd both be coming from the left and stopping at the first number. So after I multiply these two, 7.20 times 0.5, in your calculator, it comes out to 3.6. It actually changes it for you in this case. I don't want you to be confused. We should actually leave it as 3.60 and then go, hey, 0.50 only has 2 sig figs. I need to round this number down to 2 sig figs, so I'm going to get rid of the 0. It's not that I'm getting rid of it. I look at 6. I look at the 0 next to it. I'm not going to round up, so my answer is 3.6 in the end. Okay? So it's you solve, you calculate it, and then round to the least number of sig figs. Just to point out, and I mean, this is where your calculator can trick you. Whoops, I just erased a bunch of stuff. Let's get back. There we go. If this was 0.500, okay, sorry, let me try to erase some of this. If this was 0.500, that means both of them now have, sorry about this, I'm making a mess here. This has 3 sig figs, this has 3 sig figs. I'd actually have to write 3.60 as my answer, even though your calculator will say 3.6. Your calculator does not do sig figs. Okay? Let's go to the next one. I have 4 sig figs here. Comes from the left, all of them are kept. 6.1 comes from the left, all of them are kept, but that's only 2 sig figs. So 24.32 divided by 6.1 comes out to 3.986885246 in your calculator. Now you don't need to go up to your teacher and go, what should I round it to? Excuse me. I'm going to round it to 2 digits. 1, 2. The thing is, it's going to be 3 point, but I have to look at the 9 and look at the number next to it. It's an 8. That means it rounds up. So actually, this comes out to 4.0. Okay? Next one. I have 3 sig figs and 1. So this is going to have to come out to just 1. So 6.02 times 4 comes out to 24.08, but I need to round this down to 1 sig fig. I need to keep just the first digit. The thing is I have to look next to it. It's a 4. It's going to round down, so this will come out to 20. That's where some of this gets a little bit weird, because you're going to be like, wow, that's not what 6 times 4 is, 20. But if we're going off of sig figs, that's what it has to end up being. 22.4 divided by 3.146 comes out to this whole giant mess, 7.120152575. 3 digits, 4 digits. I'm going to keep 1, 2, 3, but I need to see if I need to round this last one. It's a 0, so no, 7.12. Okay? So again, it might be something you have to go back and watch me go through some of those a little bit more. Okay? Last thing, pretty quick here, is accuracy versus precision. Okay? Accuracy is saying how close are you to the actual true value. That's what accuracy represents. So if I have a dartboard, you have your bullseye in the middle, you're accurate if you keep on hitting or you're getting very, very close to the bullseye. That's what accuracy is. You're close to what it should be, what you're aiming for. Precision is more about that when you throw all those darts, they all end up in the same place. You don't have to be on the bullseye, but if all the data is very close to each other, that is precise. Okay? To show you not precision, okay, not precise, okay, you could be not precise and accurate. You could basically be, there's one right there, there's one right there, there's one right there. If I average all 3 of those together, my average spot would be right there. Am I ever hitting the bullseye? No. But if I average them out, it could basically look like you're surrounding the bullseye. You're pretty close. Not precise and not accurate, that would be where you're just all over the place. You're missing the board too. Okay? So that's where you're just, it's just so random. You don't know exactly where you're going with it. All right? So we're going to be doing that some in terms of looking at your data and going, are you accurate? Are you precise? Because if you're precise, you know your technique is very good. Like people that are able to get all the spots right there, your technique is good, and maybe there's something wrong about the equipment you're using. All right? I don't know if anybody's gone to a gun range and fired a gun where the sight could be off. Okay? And you could be always aiming straight at the bullseye, but every single time it hits just a little bit off. All right? It's not saying that you're bad, it's the equipment is just off a little bit. Accuracy would mean, hopefully, one, well, you don't have to be precise, but obviously accuracy means you're just getting what the actual value should be, okay? And hopefully you're repeating it and getting it over and over again, and then you're both accurate and precise, okay? So just 2 little things with that. There is a calculation to basically say how accurate are you. It's percent error. You always do the absolute value of your experimental value minus the theoretical value. Now, textbooks use different terms for this. Experimental value is what you are doing in the experiment. So sometimes this is considered your value. What did you get? And then you subtract that from the actual value. What are we hoping we should get? That's what we mean by theoretical. And then you always divide by theoretical. Okay, you always divide by theoretical. Since this is an absolute value, you don't have to worry about whether it's experimental minus theoretical or theoretical minus experimental. Okay, this is going to come out to a positive number. But then you multiply that by 100, and that would be your percent error. So let's just look at a couple problems here real quick. All right. If I look at these situations, okay, we would say this is what you're trying to get. You're trying to, the actual value should be 2.701. Okay, or we'd probably reveal that at the end of the experiment. Group A here got 2.001 in their first trial, 1.999 in their second trial, and 2.000 in their third trial. What can you tell me about them? Are they accurate? Are they close to the real value? The answer to this would be no, based on percent error. We could do a percent error calculation and say, usually when we say you're pretty accurate, if you're only within 10%, 5 to 10%, you want to be less than 10%. But you can say that the group A is precise. They are precise but not accurate. So maybe there's something wrong with the instruments they were using, the equipment they were using, because their technique looks good. The second group, 2.6, 2.7, 2.8, they would be both precise and accurate. Precise and accurate, because if I take an average of all three of those, they're basically getting an average of 2.7. The average for the first group would be 2, so they're pretty far off. The last one, well, you can already see that they're not precise. None of the numbers are even close to each other. Okay? I'd be coming back and going, what is happening with this group right now? We're all over the place. Okay? If I take an average, this is where it's weird. Sometimes it's so random where people can actually come out on the right, at the right number. But again, there's usually some issues with it. They're getting an average value of 2.5 grams per milliliter, which means they actually have less percent error than group A, but they are not precise. And I'd actually be more concerned about this group than group A. Okay? Either that, I mean, it's possible group A just consistently read something incorrectly, but was so consistent with the incorrect reading that happens. All right? If I want to do 1% error calculation just to show it, I'm going to use group 1. It would be 2.000 absolute value minus 2.701 divided by 2.701 all times 100. And so this should be 0.701 divided by 2.701 times 100. They actually have almost, let me go ahead and do the sig figs here. 4 sig figs, 4 sig figs, or 4 sig figs, so I need to round this to 4. 25.95 percent. So they're 26% off, which is pretty far, but we'd probably be able to figure out that there's something wrong with the instruments or the procedure. That's another reason behind it. Okay, so that's basically it. Hope you guys have a great day.